Hello everyone. In a way, we don't really need any special equipment today because what we're going to talk about today is this stuff, this mixture of gases that's all around us called the atmosphere, and also just in passing the atmospheres of other planets. And this is on the AQA GCSE chemistry syllabus. There's a lot of things on there that are a bit surprising, but I think that's all well and good because, you know, you don't want to be boring, do you? Okay, so the air on this planet is proportioned like this. You can see that most of it is nitrogen. The nitrogen is 78% of the atmosphere. This is by mass, not by volume, although the mass of nitrogen and oxygen is very similar. Nitrogen doesn't do very much, it's quite inert, provided it's in the form of molecules. Atomic nitrogen is actually very reactive and you can make explosives from it. 21% is oxygen. That's that bit there. Oxygen is more reactive, but it's next to nitrogen in the periodic table, so it's actually very similar in density. The next one along, okay, that's almost all the atmosphere. Then you've only got about 1 and a bit %. Argon's the next one, that's 0.93%. Argon is a noble gas, and there is in fact, I think, only one compound has ever been made from argon, so it doesn't do anything. And it's been used to fill incandescent light bulbs, filament light bulbs, so that tungsten doesn't oxidize or get damaged by reacting with the other gases in it. And it's also used in double glazing. I'm not sure why that is, but it is anyway. All the rest, firstly, you might notice that carbon dioxide is actually very low. Carbon dioxide is something like 0.003%, and the others, water vapour, that goes up and down, that varies. Krypton and xenon are in tiny traces. Xenon is probably the most expensive of all the element gases. It actually costs more weight for weight than gold does. And then you've got helium and radon, which vary. Radon is created by elements breaking down in granite, so it's high in granite areas such as in Great Britain, around Aberdeen and in Cornwall, and that's a very heavy gas and tends to build up in basements, and because it's radioactive it will also tend to cause lung cancer when it's breathed in, so it's not very safe. And helium, the other one, there's not much of that. What helium is actually the alpha particles which are created by radioactive decay. When 2 protons and 2 neutrons break away from a radioactive element, an atom of radioactive element, they then ionize, they get surrounded by electrons, and they turn into a helium atom. But helium atoms move so fast and they're so light they just zoop up into space, and there's hardly any of them, although they do tend to build up in traps like natural gas traps and so forth, so you do get them sometimes. Right. Now, if you wanted to conduct an experiment to determine the oxygen content of the atmosphere, this is what you might do. You've got, start from the other end, sorry, I'm seeing this backwards. You've got 100 ml of air in a gas syringe. A gas syringe is a very well designed syringe, very well sealed, so you don't get any leakage from it, and it's used for measuring gases and containing gases. So you've got 100 ml of this mixture of air, and let's say at normal temperature and pressure, so say it's at room temperature and at sea level. You then push that down and drive it through a container, which will of course contain some air in itself, which is almost filled with copper granules. You heat that up at the same time, and what you will find, or what will happen, is the copper granules will combine with oxygen and you'll get copper oxide. You can't use coke or coal or something like that because that will release carbon dioxide. The reason you use copper granules, and you could use other things like for example magnesium, is that it oxidizes without producing any waste substances or gases. So what you'll be doing there is you're going to remove the oxygen from the air. You push it out the other way. Now by this point, firstly it will have picked up some of the air in there, and also it will be hotter, and because of Boyle's laws, the gas laws, because it's hotter, it will be larger. It's very easy to work out what the expansion of a gas is because it's basically a 273rd of its volume at 0 degrees centigrade for every degree centigrade that goes up. And that's the same for all gases, which is quite surprising actually. I always find it a bit strange that gases expand at equal rates like that, but they do, and they're always the same density in terms of particles per unit volume as well. So what you'd end up with is about 80 mil of a mixture of nitrogen and argon and a few noble gases at the other end, although you would have to call it to room temperature to measure it accurately. So that's that. Now, the atmospheres of other planets in the solar system, no, actually I won't say that yet. If you want to extract oxygen or other gases from air, the way you do it is you cool it down and they come out of solution. They come out of the mixture because they have different boiling points. So, for example, you cool it down and you get oxygen because it's condensing, but not argon condensing at a lower temperature and that sort of thing. So you can extract, including dry ice actually, which is frozen carbon dioxide, which has no liquid phase, by the way, at normal temperature, normal pressure rather. You can get them to condense and separate. Now, oxygen obviously is used to support combustion and life, and nitrogen is quite useful because it doesn't do that. And if you look at my half bakery video, which I'm going to link to here, that's fill your home with nitrogen, which illustrates what happens if your home was filled with nitrogen. But in a home that's filled with nitrogen, you would find that your food would take a very long time to go off, you wouldn't have any fires, and you suffocate. But it'd be a nice way of dying in a way because you don't get the struggling and the panic that you would get with carbon dioxide inhalation. So it has been suggested, and I don't agree with the death penalty, but it's been suggested that the most humane form of death penalty would be to force the person to breathe nitrogen, because then they would just pass out without any triggering of the panic system that is supposed to stimulate you into looking for oxygen. So yeah, there's that. Bit of a depressing subject, isn't it? Right, now as far as the other planets are concerned, their atmospheres, I'm talking about Venus and Mars here, i.e. the rocky planets that are near the Sun, their atmospheres are mainly carbon dioxide. Mars's is 95.3% carbon dioxide, although the pressure on the surface of Mars is only 1% of the pressure on the surface of Earth, so actually that's only 1/100th of the amount of atmospheres we've got anyway, so it sounds like a lot, but it's actually not that much. 2.7% nitrogen and 1.6% argon, so it's got slightly more argon than we have. And in fact, just as it does on Earth, the atmosphere of Mars has a greenhouse effect because of the carbon dioxide. It is actually a lot warmer, even though it's bloody cold, it is actually a lot warmer than it would be otherwise. And it actually does get up to about room temperature in the middle of summer on the equator on Mars, so it's not that cold. The contrasting planet Venus is 96.5% carbon dioxide and has a density of atmosphere which is equivalent to the pressure of water nearly a mile down in the sea, in other words about 90 times our pressure, and 3.5% nitrogen with a trace of argon. And it's 3.5% nitrogen because that actually reflects what the atmosphere used to be like before the photolysis and the greenhouse effect drove all the carbon dioxide out of the rocks. So that's where it comes from, and that's where it went in our atmosphere. Most of the carbon dioxide was absorbed by carbonate rocks like limestone, and there's another video on limestone, very boring one of course, here. And so that's where it went in from our atmosphere, and it also got absorbed through the process of photosynthesis and getting packaged into fossil fuels. And of course there's a fossil fuel video on this playlist as well, which is here. And that didn't happen on Venus, and in fact it got released from the carbonate rocks. So that's where it went. The oxygen in the atmosphere now didn't used to be there. And this is where we get onto the Miller-Urey experiment, which, believe it or not, is also on the AQA syllabus. And I know I keep going on about it, but I've actually got an excuse now. Here's Miller-Urey. Miller-Urey experiment was a way of attempting to create the basic building blocks of life on the Earth, and it was done in, I think, the 1950s by Miller and Urey. What they did was they got the following gases, that's hydrogen, ammonia, methane and carbon dioxide, and they got water and they boiled it. This is all completely sealed in, and the water boiled and it got sent round there, that's where the steam's going, and then goes into this mixture of gases here, through which a high voltage spark, which represents lightning, was passed, and they got the basic building blocks of life, such as amino acids, such as glycine in particular, and a lot of other things which they hadn't detected at the time because they didn't have accurate things, basically something like 20 amino acids, which is all you need for life. And they condense that, just need to cool it down there. So just running through a few of the uses of the gases in the air. Oxygen is obviously used to support combustion and enables us to breathe. Nitrogen is used to preserve things. Carbon dioxide, carbonating drinks, and it's a greenhouse gas, of course, and there's a lot of people say there's too much of that in our atmosphere at the moment. So that's it. That's the end of Big Science Goes Global for today. If you like this video, please rate, comment, share and subscribe. If you dislike this video, please tell me why so I can improve, and I'll see you tomorrow, or if you're following Big Science, then next week.